Hey everybody! Let me just get some little things set up here. Where's my clips? Dude, that's Open Tunes. Why is that Open Tune? There we go, there's my clip. They're doing like a real lecture. Let's like actually make this look a little nicer. Why not? There we go. We got something in chat, right? Can we do a damie, can we get a damie emote in here? Oh, hell yeah, never mind. Thank you, Egg, for making me not have to test chat myself. Hope my week has been good. Pogtuber, did I see the Reddit post I sent? I'm trying to think if I did. Maybe? Was it a while ago? Let me see. Let me like run around in circles here. Did you just DM it? Oh, I did see this. Yes, I did. It's awesome. I love Germa. I love Germa. My big fan. My big clown. My big clown man. He's not big, or really a clown, but in my heart he is. I don't really have too much of a plan for today. I mean, I do, but like, we might just fuck it, we ball a little bit. I said I would start at 2:10, but I'm gonna give people a little bit more time to get in. So I think, yeah, I think we'll do, well, I can at least like write out what we're gonna do today. I'm thinking we start with like vectors. I think we just talk about vectors, we talk about linear combinations and linear independence, and then that can kind of lead us into matrices. And we can talk about what a matrix is, dimensions, what rank is, what else? We can talk about finding inverses. Lots of other kind of cool matrix stuff. And then I think we can get into, oh, we can also, so we'll do like basic matrix stuff, and then we can do eigenvalues, or we can just talk about eigen things. Come on, tablet. I need to replace the nib on this. We can do that right now, actually. Eigen stuff, and then I guess we can start talking about differential equations. And we should probably start by doing, oh, we can talk about diagonalization after that, and then we can do, sorry, I'm trying to like open this at the same time while thinking of stuff. Okay, that nib just flew off into the ether somewhere. I don't know where that went. Uh-oh, well, it's fine. Do I have any fresh ones? I do. Ooh, I could put a gray one in. Should I put a gray one in chat? I don't think I've ever had a gray nib in my head. I can do it. Ooh, it's so fancy. You can't see it. I like my little inkwell. I use it a lot. And do we have labs on the first week? In math class? If I can think of a... Oh, you know what? I can spill little beans. I really do want to do labs at some point. I want to set up VR chat labs. But I don't know how coding them would work. But I think it would just be so fun to do like an actual lab, like a physics lab in like VR chat. That'd be so cool. Me being a nerd. But then I need a 3D model, and I don't have time to make a 3D model right now, so probably won't be for a while. Okay, let's see if that helps. Okay, so we have eigen stuff, and then we can start talking about like, oh that helped a lot. Diff-EQ, 3D damie cheese. He's gonna be so flat just for you, Egg. He's gonna be like a board. He's gonna be he's gonna have negative ass, like this. I don't even know. That's like how do I even draw that? Negative ass. If we talk about basic differential equations, so we can talk about homogeneous and then non-homogeneous, and then could you drink one like a cistern? Like you just lie on the ground and just like collect water. Oh, that's so scary. Oh god. Hi, Umbra. I'm sorry, I'm also a little sick, so I'm kind of nasally. So we can talk about that, and then we can talk about systems of differential equations. Oh, I guess we could also talk about, like, first order linear. Lin, and that's like, what is that? That's a fucking mu integration. And separable? Okay. I think that's everything. Also, I'm trying new tracking. I'm trying because VTube Studio got an update, the Google media pipe. I don't know, it's Google tracking. So my face is powered by Google today. Oh, everything's just lagging. Okay. All right, we're just gonna start with some vectors. All right. Oh, starting it is weird. Okay, hey everybody, it's me, Damie. Today we're gonna be doing lots of linear algebra. Don't know how long this will go on for. I kind of don't assume we will get to differential. We might get to like just the start of differential. And we can talk about that. Oh yeah, okay. Yeah, there's a lot to talk about there. But we're just gonna start with some basic linear algebra. And we're gonna start with some vectors. So hopefully everybody here has heard of a vector. If you haven't, a vector is it's like a line, but it's like a little part of a line. It has a start and it has an end. It has or you can say it has a start, it has an end, or you could say it has a direction and a magnitude. So usually we define vectors by where they end with respect to the origin. So there are lots of different ways you can write vectors. Some people choose to describe them in terms of the unit vectors. The unit vectors are special vectors that point one unit in the direction of each axis. So the one that points one unit along the x-axis is sometimes called x hat, like with a little hat over it, or sometimes it's also called I hat. I don't know why. I like x hat a little better because you can see it, it's like x. And then that means that this one would be up here, this one would point this way, and that would be y hat, or j hat, sometimes it's called. So every vector that's in this space right here, like in 2D, can be represented by these two vectors, if you think about it. Because we can stretch this vector over here to this point, and we can stretch this one up here. And if we add them for vector addition, you take the tail of one of the vectors. So if you had a vector like this and a vector like this, you take this vector's tail and you put it on the tip of the other vector you want to add it to, and then you draw from the tail to the tip, and that is your resultant vector. I'm going fast because I'm assuming that people kind of have already seen vectors before, hopefully a little bit. But this idea where we're adding vectors together to make other vectors is a really fundamental part of linear algebra, and also just using linear algebra to solve stuff in general, because if we're adding certain things together and they can make a bunch of different things, that's a pretty good way to find a set, right? Like a generalized answer to something. So we can kind of see how this might be like, oh, you know, if we were to say, have a bunch of vectors that we wanted to represent in this plane, right? This like 2D plane, or if we wanted to represent every vector in this plane, that these two vectors, this one here and this one here that point along the axes, might be able to help us do that. And we don't know necessarily if that is the only way, but we do know that like if you take the vector, and the way you write vectors is you can write them with these little caret brackets, where you put the x coordinate and then the y coordinate. So that would be equals x hat, and then this would be equals y hat. That these two vectors might help us represent things. The way that we're going to write vectors for linear algebra, and you'll see why in a little bit, is we're going to write them as a column. And this is kind of weird, but we can just imagine that we're kind of turning this vector to the side. So if we wanted to write x hat as a column, we would write it 1, 0. That equals x hat. And we write y hat as 0, 1. And that's y hat. So the generalized form for like a vector in 2 dimensions would be your x coordinate and your y coordinate, and that equals some vector v. And the way we denote vectors is by just putting a little arrow over the top of them. Okay, so we know stuff about vectors. Now we want to know, let's see, well, what kind of stuff do we want to know? Well, one question might be, if we say this is a vector v, we want to know if we add two vectors, like let's just... I cannot tell you how excited I would be if I got a properly power limited USB hub. Maybe I will make a throne and specifically put that on it because of how much I really need to not just spew hell noise into people's ears. It's so bad. I'm so sorry, guys. My computer. God, in a week or so I'll be home and then I won't have to deal with Demon Damie. Okay, sorry about that. The demons won. They were just so excited about this concept of adding vectors together. So sometimes we'll have a vector that like goes over this way, and we'll have a vector that goes, if I can draw it right, goes over this way, and one that goes over this way. And you know, maybe we want to figure out if we take these vectors and we add them together, can they equal this vector over here? Now, it's pretty easy to tell, you know, if we have A and B be like, you know, 1, 2, and like 3, 4, and our V is, you know, 2, 3. We can just look at that and say, well, you know, 1 plus 3, this is going to equal 4, and this is going to equal 6. That doesn't equal that. But what if we made this problem a little bit harder, and we decided to say that any part of A and any part of B, can that ever make up this vector? And that's a really useful question because it's sort of asking like, can this direction plus this direction ever go in this direction? Depending on how we do it. So the way that we're gonna do that is by putting a constant in front of it. So we're gonna say a constant times A plus a constant times B equals a constant times V. Or just V. It doesn't really matter, right? So solving this is like a little bit trickier, but let's do an example. I'm just gonna make one up. It might, I don't know how it's gonna turn out because I'm gonna make it up. So let's say our A equals, let's do 1, 2, and B equals 2, 3. And then we'll say V equals 5, 6. So we'll have C times, sorry, these really should be C1 and C2. C1, right, because we want to have two different constants. It's not just necessarily the same thing. C1 times 1, 2 plus C2 times 2, 3. We want to know if that's equal to 5, 6 ever. Or, you know, what these constants would have to be to do that. So, all right, if we use our rules, right, for vectors, if we multiply this out, we're going to get C1, 2C1. I'm just putting this one in there. And then 2C2 plus 3C2. And that's going to equal 5, 6. So now we can kind of see a little system forming, right? We have two equations here, because we know in the same way that, like, if we were to add these two and see if they equaled 5, that this one plus this one has to equal 5. So we'll have C1 plus 2C2 equals 5. And 2C1 plus 3C2 equals 6. So there's a couple different ways we can solve this, right? If we just know about substitution, then we can do that. And I'll do that way for now. So C1 equals 5 minus 2C2, and then we can plug this one in here, and we'll get 10 minus 4C2 plus 3C2 equals 6. So 10, or let's do minus, that'll be minus C2 equals minus 4. So C2 equals 4. And C1, then this will be, right, this will be C1 plus 8 equals 5. This equals negative 3. So it turns out these vectors do add up to make this vector over here. So if we multiply 4, and if we take minus 3 of the first one and 4 of the second one, we'll get this. And what this is called, this kind of question, is we're saying that vectors A and B make, okay, that's a bad way to put it, that vector V is a linear combination of vectors A and B. So it's called a linear combination because we're taking them and we're just adding them. That's why it's linear, right? We're adding them with constants, and it can create V. So there are lots of different vectors, right, that V could be a linear combination of. Like, for example, V is a linear combination of 5, 0 plus 0, 6, right? So there's not only one thing that can make up a vector. It can be lots of things. But that's usually the first question we ask about vectors, because when we are looking at space, right? Now this is kind of more into the matrix side of things, but in linear analysis or linear algebra, you want to talk about spaces or sets, right? So sometimes we'll have a lot of vectors and we want to describe those vectors generally. So, you know, we might have a set of vectors that's defined by some A here, and like any A, and then the second component is 1 always. That's not a very good one, but so that's a set of vectors, right? This is defining some vectors, like the vector 1, 1, 1 lives here, the vector 0, 1 lives here, the vector I1 lives here, right? It could be a complex space. And when we're defining spaces, there are some spaces of interest that are useful to us. And we'll get to those in a little bit, but just know that when we're defining spaces, in the same way that when we're defining systems, right? If we have like three axes of movement, in order to find, you know, out where we are in that system, we want to restrict all 3 axes, right? If we wanted to have our solution be like a point, we have to make sure it can't move in any of these directions. But if we wanted it to be a line, we have to make sure it can't move in this direction and this direction. That may not make total sense, but the idea is that we'll be using linear combinations to try and find vectors that are different than each other. So when we're defining a space, like let's say we want to define just a 2D space. And let's try and define this with some vectors. What's the best way to do this? I'm trying to think about the best way to think about this. If we wanna, okay. We've seen that these two vectors, x hat and y hat, or I hat and j hat, they're more commonly called I hat and j hat. These two vectors can make up any vector in two dimensions, right? And for reference, two dimensions is sometimes referred to as R2, because this is like the real numbers 2. So then 3 dimensions would be R3, etc. So if we want to define this space, we know that the vectors 1, 0, and 0, 1 can make up any vector in this space, right? And that kind of makes sense because if we take a constant times 0, 1 plus another constant, 1, 0, 0, 1, then we can make any vector that lives in R2, right? Because we'll just have A, B. And that, by definition, is any vector that lives in the space, because 2 different numbers. But, you know, there might be other ways to define this space, right? This is called the standard basis, or just like, basically the most standard way you can express this, because it's just 1. And if we wanted to find the standard basis for R3, that would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Because these are the simplest vectors that you can take to get that any vector that lives in that space. But we want other ways to define it, just because that might be useful to us, or also because you know, maybe we have a system and we just want to define our coordinate plane in a different way. Like, can we use something? Can we use an axis instead of the axis that's like this in the Cartesian coordinates? Can we use an axis that looks like this? Like, is that okay? You know, if our origin is at the same place but it's rotated. And, you know, it's a good question to ask. So one of the things that's going to help us with that is that we need to figure out a way to make sure that our vectors aren't giving us the same information. So in this case, these vectors are pointing completely in 2 different directions, right? And adding them, those components can make any vector in space. So the important part here is that they're different from each other. And this makes a little bit more sense in R3. So if we take a look at this vector here, this will be x, this vector here, this will be y, and this vector here, this will be z. If we do x plus y, there's no way that it can ever equal z, right? So z is not a linear combination of x and y. And this is really important because if z were a linear combination of x and y, like let's say it was 1, 1, 0, or let's say it was 1, 1, 1. No, that wouldn't be it. Say it was 1, 1, 0. And we were trying to define a space with 1, 1, 0, 0, 1, 1, 0, 1, 0. We have to think about which axes we've locked, right? Okay, so we know that there's something going this way, cool. We know that there's something going this way, cool. And we know that there's something going this way. Okay, so we know that we can't move in this direction at all, or in this, you know, we can move in those directions. But the issue is we haven't really specified anything about z. Like, we can't go up because there's no vector that's telling us we're allowed to go up. So we've just created this plane right here instead of the whole space that we wanted to define. So it's really important that we have 3 different vectors to define a space that is that dimension. So there's a theorem that says for any space that's n dimensions, you need n vectors, which are not linear combinations of each other, to be able to define it. So, and that goes for any, it could be a space within another space. And now that sounds kind of crazy, but if we take a look at this plane right here, and we look at this first example we did, you'll see that they're actually the same thing, right? Like this is the R2 plane, but the whole space is in R3. So if we wanted to define a plane, that's totally okay. We can just define a plane. So we'll need 2 vectors to define that 2-dimensional space. And if we wanted to make a line, like here, then we just need 1 vector. And that defines how our space exists. So in that vein, let's talk about how we make sure our vectors aren't linear combinations of each other. So one way you can do it is, and it doesn't really work at higher dimensions because as soon as you get to having 4 vectors, you just have to do a lot of calculation. But you could, for a 3-dimensional space, like let's say you have a vector A, a vector B, and a vector C. If you want to figure out whether they're not linear combinations of each other, okay, so you'll say A. Okay, so does B plus C, does some constant times B plus some constant times C, will that ever equal A? And then if the answer is no, you're good. And you do the same thing for B. So some constant times A plus some constant times C, does that ever equal B? And if it's no, then you're good. And then you do the same thing for the other one. But that takes a long time, right? Like we had to do like a whole little substitution thing to figure this out. And that's really not great. So we need to find a better way to do this. One of the ways we can do this is by using a matrix, and that kind of nicely transitions into our next topic. So let's set this up first. So let's say there's a vector A, and a vector B, and a vector C. We want to figure out if these are what we call linearly independent. So we had linear combinations, which was asking if a certain vector V, did that equal sometimes a vector U plus sometimes a vector W, right? But now we're going to talk about linear independence, which is asking about a set of vectors if they are or aren't linear combinations of each other. So if they are linear combinations of each other, then that's a linear dependence. If they aren't combinations of each other, then that's linear independence. And that means that we have 3 vectors that tell us, or n vectors that tell us n different things, different pieces of information. Okay, so we gotta figure out how to do this. So let's do A equals C1 times B plus C2 times C, and to keep it simple, we'll just do it in R3. That's normally where we'll live. So then B equals C1 times A, or I should probably, we'll do it C1. No, we gotta do it C3 plus C4 times C, and then C equals C. Oh, my naming convention is falling apart. A plus C6 B. Now let's expand this out here. I'll just do it for 1, and then we can kind of see where this is going. So for A, we're gonna have A1, A2, A3. Oh no, my naming convention truly is going to fall apart. Let's call this D. There we go. And that's gonna equal D1, B1, D1, B2, D1, B3, plus D2, C1, D2, C2, D3, C3. So that gives us D1, B1 plus D2, C1 equals A1. And if we continue this, we'll see that we get D2 plus D3, D2, D2, or sorry, D1. D1, B3 plus D2, C3 equals A2 equals A3. And then we can go about solving this, but obviously we can't because we don't have enough information. But from these other ones, we can get those information chunks to be able to solve it. It just looks kind of crazy. Let me pull this over to a new little thing here. So if we were to do this for all of them, we'd get something that's like D3, A1, plus D4, C1, D5, C2, or D4, C2, 4, C3. I'm trying to think about how you pull this together. Oops, D3, A2, D3, 3. There's a way you could pull it together, and I don't remember it because most people don't prove it. But basically, all of these equations that you get can be simplified down into a matrix of a couple equations. So what you end up doing is saying the first component of A, second component of A, third component of A, and then for B, you do the same thing. And for C, you do the same thing. Oh, I know. Okay, I know what it is. I lied. I lied, gamers. I lied about this. You can do that, and that would actually work out if you like divided everything up. But the other easier way to say linear independence, I can't even believe I lied to you like that, is okay, you say this. I don't know why I lied. Oh, I got scared, okay? I got caught up in the lecture. Okay, you say this. You say C1 times A plus C2 times B plus C3 times C has to equal 0. And you say, Damie, how does this test for linear independence? You said that they had to be not combinations of each other. What this is saying is that for this to equal 0, this constant here, and this constant here, they all have to equal 0. So if we solve this somehow, and all of these constants don't equal 0, then we have a linear combination situation, because that means that like let's say A is 0, right? This goes away, but then C2B plus C3C equals 0. If we had true linear independence, right? Like let's say we know these two are linearly independent. There's no way that they can like cancel each other out to 0, right? There's no way you can say 1 minus something times 0 equals 0. It doesn't work because it's 0 here. So if we had this, then that means that this could be something like 1 minus 1, 0, and then 1, 1. That would be bad, right? Because then, or like let's just say minus 1, 1. Then some combination of these two can go to 0, and that's not good. And also this is a 0 vector, which is literally just like 0, but it's in a vector. So it would look like that, or however many dimensions you had. Okay, sorry if that was very confusing. That was probably incredibly confusing, because I didn't do it the right way first. Okay, but what this is saying is that we have, this is how you get the matrix. Okay, so we're gonna turn this into an equation, right? So we'll do C1, A1, C2, A2, C3, A3, plus C2, B1, C2, B2. Why did I change the constant? C3, B3, C2, B3, plus. Okay. Equals 0. So now we see that we get C1, C1A1 plus C2B1 plus C3C1 has to equal 0, and the rest of these also have to equal 0. So we can factor out, these constants actually end up not mattering in the matrix that we construct, because it just matters about these, not about the actual values of the vectors, not the values of the constants in front, because we can just pretend that they're whatever we want to pretend them to be, because it should work for any number, right? Like if we put any, they're all going to be 0, right? So we can just ignore them because they should be 0. So then we can construct our little matrix, and then we can start talking about matrices. And I'm just going to write it out real quick, and then maybe you'll go, what? Or maybe you'll go, yeah, I know what this is because I know what a matrix is, you silly catboy. But we'll have something that looks like this. Okay, so let's talk about anatomy of a matrix, and just like matrices in general. So a matrix is like a vector, but like level 2, kind of. It's like a bunch of vectors stacked up or stacked on top of each other. We have a certain number of rows which go across this way. These are the rows. And we have a certain number of columns that go across this way. Matrices are usually defined by, so this is a 3 by 3 matrix. But you can also have, if we want to describe this one, these ones up here, these would be a 3 by 1. So you always write row by columns. That's how we write them. Inside a matrix, you can add matrices just like you can add vectors. Vectors are actually a type of matrix, right? You can see that this is a 3 by 1. This vector too, like if you had 2, 0, that's a 2 by 1 matrix, right? So we can add them. We can put a scalar multiple out in front and like multiply that into every value. But matrices are also a little special because they represent, a lot of the times they represent systems of equations, right? Like we saw with this one. If we were to expand this out, what we're saying is A1 plus B1 plus C1 equals 0. And the same for each other row. So they represent relationships between equations. And just like we can manipulate systems of equations, you know, like if we had A plus B equals 3 and B minus A equals 4, we can do different, there are a couple different operations we can do on matrices, just like we can do two systems. So if we were trying to solve this system, not by substitution, but by you know, doing things to it, one thing you can do is you can add these rows, right? So if we were to add these, we would get 2b equals 7, b equals 7 halves. So we can add rows together, add rows to other rows. And in this case, right, we don't write out the whole system again. We can just write this out and like look at this little thing because that's, you know, we canceled something out. But you can, when you're doing it in a matrix, if we wanted to add two things together, we would say like row 1 plus row 2. We could say A1 plus A2, B1 plus B2, C1 plus C2, and then we would keep row 2 and 3 the same. So we can add rows together. Another thing we can do is, let's say this was 2A, 2B. We can multiply, right? Or divide, which is kind of just the same thing as adding the row to itself, or subtracting the row from itself, right? So we can multiply a row. So if we wanted to divide this by 2, then we would have A plus B equals 3, A plus B equals 2. This doesn't exist, obviously, because A plus B equals 3 can't equal A plus B equals 2, so we've just made an unsolvable system. But that's okay. It's fine. We can see examples like this that might crop up later, and we can kind of see what that tells us about the solutions and what the values of A and B might be. But so we can multiply things. And the last thing we can do is we can permute. So this will come up when we're trying to find a very special form for a matrix. But you can just switch two rows. You can't switch columns, but you can switch rows. So you can just switch this, like row 1 and row 2. You can just swap them. Those are three things. So we've got add, multiply, and then swap. Three things. Pretty simple, but very useful. So let's actually put some vectors in here. Let's see if the vectors 2, 1, 4. Let's say 6, 3, 8, and 0, 1, 0. Let's see if these are linearly independent. So we're trying to make sure that when we add these up, that there's no way they can equal 0 except for them equaling the constants in front of them equaling 0. That none of these are able to add up to versions of themselves. Okay. So we're gonna start by plopping into a matrix, and then we'll see what we can do from there. 2, 1, 4, 6, 3, 8, 0, 1, 0. Now it's like, okay, we've got it in a matrix, cool. What the hell do we do with this? So when we're solving a system, because we're kind of trying to solve a system, right? We're trying to solve the system for the constants in front of this, C1, C2, C3. We want to see if those are all 0. That's what we're solving for. When we're solving a system, kind of order we want to get, right, is, in this case, C1 equals something as one equation, C2 equals something else, and C3 equals something else. So if we were to translate this in the same way that we wrote out this, and you can write it as A1 plus B1 plus C1 equals 0, if we were to translate just this equation into a matrix, this top one, it would look like, okay, so we have 1 of C1, right? We have 0 of C2, and 0 of C3. And for this one, we have 0 of C1, 1 of C2, 0 of C3, 0 of C3, or sorry, 0 of C1, 0 of C2, 1 of C3. So we get ones down the diagonal. And this is a very special matrix called the identity matrix. It's sort of like the number 1. It can do a lot of special things. A lot of the time, we'll use this matrix to prove that things equal other things, right? Because it's like multiplying things by 1. Or when we want to take a number and turn it, like a single number, like a constant, and turn it into a matrix, we might use the identity matrix as well. So it's a really cool little matrix. But we are trying to get to that. And this kind of matrix isn't only a 3x3 or a square matrix, right? So this is a 3x3. It counts as a square because the rows and the columns are the same. Let me just snatch this. we're not only trying to solve systems that are square, right? Because we might not have a square system. What if we're only given, you know, what if we have 3 variables, a plus b plus c equals 7, and 3b minus 2c equals 2? What if we have a system like that? Because that'll look like, right, if we're translating this, 1, 1, 1, 0, because we have no a, 3 minus 2 equals 7, 2. And when we do this, by the way, we can take away this equal sign, and we can put that value, 7, 2, right in here. Because when we do the row operations, right, like when we do operations on a system, and we're solving it, like if we have a plus b equals 2, 3a minus c, or b equals 3, when we multiply a row, we're also affecting this number, right? So we want to make sure that this is inside the matrix. So like if we say row 2 times, or row 1 times 2, that like it's going to affect this as well. So the question is then, okay, if you're trying to solve this system, how do you do that? Like, you can't make an identity matrix. Do you just put like a 1? Are you trying to get it to 1, 1? Like, what are you doing? Great question. We're gonna try and get it to what's called reduced row echelon form. So what that means is that in every column that there is a leading 1, which is a fancy way of saying when you have a 1 that starts a column, there has to be zeros underneath it, but there can be other numbers above it. And the other thing is that you can skip places, right? You don't have to have a leading 1 in every column, but you do need to have a 0 there if it's not a leading 1. So you couldn't have this be a 2. You have to make sure that the first value in every row is a 1. So in this case, if we were just to write, you know, not care about the other numbers, but just reduce row echelon for the first part, we would say, okay, 1, 0, that's good. And we'll have to do the row operations to get these numbers to change. But I'm just gonna say like what it might look like. Or no, let's just do the row operations. Why not? Okay, so our goal is to do this. So we've got a 1 here, so that's all right. We can leave that there. Our next goal is to, well, there's a value here. So we need to make sure that this is a 1, right? That's the first value in the column, or in the row, so we have to make sure that's a 1. So we're going to divide this by 3. Row 2 divided by 3. And I always write down the row operations I do. So we'll have 1, 1, 7, 1, negative 3 halves, 2 halves, and then 2 halves. 2/3, Jesus. Okay, so we've got that 1 there. And it is okay that there is a value above it, but we could cancel this out if we wanted to. But in this case, this is actually already done, because the idea is that we can now say, okay, a plus b plus c equals 7. And then we know that b minus 2/3 c equals 2/3. And then in this case, we can say b equals 2/3 plus 2/3 c. And we can say a equals negative b minus c plus 7. And we can say that a equals, well, you see that if this canceled out, we would get, you know, this would be a little bit easier of a substitution. A equals, right, negative, what would that be? Negative 2/3 times 1 plus c minus c plus 7. So we've now represented both of these, a and b, all in terms of C. So we didn't get a solution for C because we only had 2 equations, and we'll see that the number of equations you have will relate to the number of, well, we'll get to that later, but number of equations you have relates to the number of like free variables is what they're called in your final solution here. So we have 1 free variable because there's nothing that's telling us what C is, and A and B are defined in terms of C. One other quick thing is that sometimes people call these leading ones, right? The ones that are leading the rows, or sometimes people call them pivots, and sometimes people will circle them. So if you see ever see something circled, is there any STEM major who's not a cat boy? I know so many STEM majors who aren't cat boys. Moment of silence for all the STEM majors who aren't cat boys. I wish there were more cat boys in STEM. We need more girl bosses in STEM, and we also need more cat boys in STEM. That's what I'm saying. Well, I'm gonna take a little drinkos break. Because I'm going, honestly, not too bad to cover in an hour to get through all the way up to reduced row echelon form. And constructing matrices. There's some other vocab we could do. This matrix is called, this whole matrix is called the augmented matrix. And this matrix over here, the one that we had from before, this is called the matrix of coefficients because it's just the coefficients of our vectors, or just the coefficients. Like if we look at this right here, that's our matrix of coefficients because it's just the coefficients, as the name implies. Okay, let's go back to the linear. I'm from high school. I don't know any stuff. It's okay. We're actually doing a. If you wanted to, you could learn a little bit. This is like just past the beginning, so if you wanted to go back and watch the VOD, you could learn a little bit. But don't hop ship yet, because it's still you can still learn a little bit if you're interested. We're still kind of in the earlier stages. Yeah, we're not at the differential equations yet. Don't worry. We're still at the linear algebra. Okay, so our motivation is to figure out whether these three vectors up here, the 2, 1, 4, 6, 3, 8, and 0, 1, 0, if they are linearly independent, which means that that multiplying them by constants, right? So if we have a times v1 plus a times v2 plus, or not a, b plus c times v3 equals 0, if that, these constants have to be 0 for this to be true. All right, so let's use our new knowledge of echelon form, reduced row echelon form, and we're gonna methodically go through this. So, just so you know, since you just showed up, matrices like this one are just a different way of writing a system of equations. So what we've just done basically is taken something that could look like 2x plus 6y equals 0, x plus 3y plus z equals 0, and 4x plus 8y equals 0. And we've just taken off all the variables and just put the numbers in here. And by solving this, we're going to be able to figure out these constants, because these are the variables we're trying to figure out, right? We've got a system of 3 equations and 3 unknowns, basically. Okay, so it's going to be a little tedious, but because you might already be able to see the answer to part of it, but we're gonna go through it. So let's start by dividing. We need a 1 here, right? If we're moving towards that identity matrix with the 1s on the diagonal. So we're gonna do 1 3, 0. So we've divided R1 by 2. And you know what? I see that down here we can also divide this out. So let's divide R3 by 4 while we're at it, because you can do multiple steps. Can I explain AVL trees? I have no clue what that is. I think you've officially gotten farther than I know about in coding. I've not done coding for a while, so. All right, now we gotta cancel out these, right? Because these need to be zeros. So we'll do R2 minus R1, R3 minus R1. And we're gonna do 1, 3, 0. So 1 minus 1, 0, 0, 1 minus 0. How do I tend to solve a palindrome problem? It depends on the problem. I'm not quite sure what you mean by that. Like, is it like asking you about constructing palindromes, or is this just a name for another problem I don't know about? This will be 0, this will be -1, and this will be 0. So as you can see here, we have a 0 here, right? But that's okay. We don't need to necessarily have that there. But what we do know is that there is a 1 here, right here. And if there's a leading 1, it has to be 1 row below the next leading 1. So this is going to be a leading 1, and we're going to have to switch it. We're going to have to swap these two. I don't remember if I mentioned that. But every leading 1 has to be right below the next leading 1, I guess is the best way to put it. Right below the prior leading 1. Let me take a look at Blaine's thing in 1 second. And then we can also just cancel out this right here. Did I actually multiply that wrong when I made this matrix? Oh, I did. That was funny. I was trying to give a... I was trying to get to... Okay. Well, so we can see that... Let's just finish this up and then I can take a look at Blaine's thing. We can look at this and we can see that this will cancel out. So we actually do end up getting the identity matrix, which means that our C1, or in this case our A, is going to equal 0, our B is going to equal 0, and our C is going to equal 0. So great job. By using these 3 vectors, we've found that they are linearly independent. What I was trying to do was make them linearly dependent. If this were a 12, that is what I was trying to do. So in that case, we would have had 3, and then we would have had a row of all zeros on the bottom. So let's take a look at what would have happened here. So I went in and I changed that. If we had 6, 3, 12. So this is very visually clearly a multiple of this one, right? This vector here. So now we've got a 1 here. There's no way to cancel out this 3. All right. So let's think about this before we just jump right into solving it. So if we look at our pivots, right? Our free variables, or our non-free variables, we've got 2 of them. So what that's going to tell us is that since we originally had 3 variables, 2 of them are defined and 1 of them isn't defined. So we're going to have 1 free variable. In this case, it's going to be this one, right? This column right here. So now that we kind of get that, let's take a look at what this would look like in terms of equations. So A plus 3B equals 0, C equals 0. So we know C equals 0, but then A equals minus 3B. So that means that V1, let's bring it down here, V1 minus 3 V2 is going to equal 0. And that means that 0 is a linear combination of V1 and V2, and we can't have that. So And if you think about it even, if we were to move C over here, right? This equals 0 equals C times V3, which this is going to equal 0 as well, right? Because we just proved that C equals 0. So we've just proved that V1 minus 3V2 equals some number times V3. So that is why they are not linearly independent. They are linearly dependent. Okay. If anybody has any questions, let me know. Because truly, I am just doing stuff. Like, I don't have a lesson plan for this, so it's not the best, and it's pretty bad, actually. So, like, if anybody has questions, and they are interested in this stuff, then please feel free to ask. Or if something is, you're like, why did you do that? Then anytime. Let me look at Blaine's thing real quick. Longest. Oh, this is just a logic thing, it looks like. Let me stare at this for a bit. I think what I would probably do is I would start with the first character. Maybe not. I think I would start with the first character and then look at go through the whole thing. Because I'm trying to think about, like, race car driver, because I feel like that's a better example. Like, so if you look at race car driver, like, all one. So if you start here, and I think maybe you just assume that the whole thing is going to be a palindrome. So you look for here, and you look for here, and you look for here, until you hit a letter. So you're like logging, you're like, okay, I've hit an R, I've hit an A, I've hit a C, I've hit an E, and the next time you hit one of the letters in here, then you have to, like, go back down the palindrome and make sure it exists. It's like, okay, so then I have the C, I have the A, I have the R, and you're like, okay, I've hit the R, which was the first one, and I know that's right. And then you would have to go through the rest of it and say, okay, so if scene.count_i equals 1, scene.count. Yeah, maybe. This might. Scene is unordered set. I think it would. Ooh, that's hard. I don't know unordered set, but, like, I think you want to preserve the order of it, because you'll have to be, like, moving through that. You want to make sure that, like, it's like you want to do, like, a stack. So you want to put your first things in, right? And then your later ones. So, like, this is 4. A hash map? I don't think you need a hash map for that. Hash maps are, like, when you have a bunch of things that you want to point to. That would be like if you had, R points to A, and then, like, C points to E or something. I wouldn't do that. I would do, like, a list. I'm not exactly sure what it would be called in, what is this? C++, but it looks like you do it in other languages too. I do, like, a list or an array. I don't any like simple array. Okay. All right. Let's talk about what we can do with this linear independence now that we know about it. How to get the longest substring? I think you just have to go through, oh, well, then you just make a count of like how long the palindrome is that you've just found, and then done it. So like if you had banana, the longest palindrome would be nan. So you'd go, okay, B, A, and you're just assuming that there's a B and an A. Oh, that wouldn't really work that well. B, okay, so you log B, you log A. Oh, it could be Anna. So you log B, you log A, you log N. You log A, and you're like, oh, there's another A, that's good. It's a logic thing. I don't know if I have the brain power to do this right now. Just because I do want to keep teaching math. And I think it would take me a little bit to think about a good algorithm for it. But I will say, I think that it is an algorithm question and it's not a coding question. It's just a how do you define the logic thing. Like a brain teaser, kind of. Okay, so we've talked about vectors. We know what a vector is. We know about how they work and what they look like. We know about linear combinations of vectors. We know about linear independence of vectors. And we know a little bit about matrices and how to work with them, and we learned about the EROs, elementary row ops, and we learned about systems, two matrices, all that stuff, and then back and forth. I'll finish answering your question real quick. Do algorithms tend to be harder than data structures? I think that both are kind of the same, two sides of the same coin, because algorithms, you do have to write algorithms, but in data structures, you just have to write data structures that fit your problem. So both of them are just like problem solving. A lot of coding is just problem solving, honestly. It's not really as much about the syntax, although you'll have a leg up if you know how to do the syntax and you know the useful things to do it with. Did I take discrete math? No. I'd like to, though. I'm thinking of doing a math minor, actually. But probably not till my senior year. Or my master's, if I end up getting my master's. Depends. I'd like to, though. Okay, so we have systems to matrices. Let's go back to the idea of spaces. Because I did kind of gloss over that. So we can define vectors as some numbers, right? But we could also define a vector as just sort of a generalized idea of like A to A, right? And we wanna define a certain word that lets us talk about whether vectors create spaces or not. And that's called a subspace. So we know that there's some big spaces that exist. Space is just a definition, a set of vectors, right? And it has to have some rules to it, is the thing, for it to be a space or a subspace. But some of the ones we do know of are like R2, that's a space. R3, another space. Rn is another space. These are all spaces, and the two things that have to make up a space, well, for these there are some extra rules, but if we're trying to make a set of vectors that is defined in R3, that is a subspace, we need these two axioms. One is that it has to be, it's called closed under addition, which means that when you add two vectors together that are both part of your subspace, the output also has to be part of the subspace. And And the second one is closed under scalar multiplication. That means that when gamers, when you multiply a vector, it also has to stay in that space. So what this ends up being is a very specific type of geometry, and these are lines or planes through the origin. And it's not a coincidence that these are like this. This is actually sort of why we defined subspaces as these things. So we can have a line or a plane that goes through the origin. And what we can show why they have to go through the origin. So if we look at this is A to A. This defines a line, right? So if we were looking at this in R2, we have some A out here, and then some 2A, so that's our line. Because this could be 3, 3, 6, this could be 1, 2. So this whole line, I'm not gonna draw that, this goes on forever. The whole line defines this subspace that we're making. Well, we don't know if it's a subspace yet, but we're attempting to see if it's a subspace. So we're gonna check if it's closed under addition. That means that if we take some vector that exists in the space, let's call it C1 to 2C1, right? Because we have to follow that. Actually, no, fuck it, we ball. Let's do AB. Let's do AA, and we want to add another vector B to B. These are two completely different vectors. We get something out of this, right? And we want to see if that is in the same form as this. So if we add these, we'll get A plus B, 2A plus 2B. And this can factor to A plus B. I'm running out of room, but we'll just write it as a boring vector. 2 times A plus B, which, if we look at our vector over here, that is absolutely closed under addition, because we've added two vectors and they stay in the same space, which makes sense. If we were to add 1 and 2, like 1, 2, and 3, 4, or something, they would stay on this line because they're going in the same direction. And if we were to multiply this by some they're going to be subspace. And we can look at that for so we can look at it for planes too, but we can look at it in a bit of a different way. To define a plane, as we saw in an example way back ago, when we were looking at that R3, right? In R3, one way to define a plane is, right, we can say a normal, and then we can say, well, this is the plane equation, But another way we can do it is we know that a plane is two-dimensional, right? So a plane, if it were to span a whole, I shouldn't say that. If it were to exist as like a whole subspace, it would be an R2. It's a two-dimensional object. So that means, and we know by that one theorem, that for an n-dimensional space, we need n vectors to express it. Express is a good word, I think. So that means that we can represent a plane as that normal and the equation, or we can represent a plane as two vectors, right? Because we have one that's going to define the direction this way, and one that defines the other direction. So in that way, it's just like two vectors, right? And we've already proven that a line through the origin is a subspace. So if we have two lines through the origin, that's still a subspace. And we can check that out. If we want to say, our space is A, A, 2A, let's do A, 2A, and B, 2B. Just because why not? If we want to add any vector in any two vectors in this space, oh, sorry, I should add a third dimension. We'll do 3A. What this is saying is that any vector in this space should be able to be expressed by these two vectors. So we'll say C, 2C, 3C, and plus, or it should be able to be expressed by this form, right? D, 2D, 3D equals, right, C plus D, 2, C plus D, 3, C plus D. Oh, you know that works because these are just, it's just two lines, right? It's just another dimension. And it works for scalar multiplication too for the same reason. Yeah. Subspaces are kind of weird. This is not a good explanation of them. I would actually like to do, I don't know, there's still some pretty decent linear algebra like books out there that are free that you can read, or, well, because Gilbert Strong actually like does good lectures and that's his job. But so yeah, subspaces, I guess we can talk about bases. So we know that we can make a space that exists within a space, right? But what we don't really know, or well, I've alluded to it, but it's a good question to ask. How do we define a space? Like, what is the best way to define a space? Because if we have a plane, right? Let's just say we have a plane, and let's make sure it's a subspace. It goes to the origin. Right, that goes through the origin. We could straight up define this by like 500 vectors. Right? Like, how many vectors do we need to put to make it be okay, right? We could put up so many. We could put as many as we want. If there is any maybe they're not even on the origin. Do we have to use can we use a vector that's like over here? Can we like, use one that's over, because these are all on the plane, right? So it turns out that there's a special word for vectors that create a space, and that is called the span of the space. So if a vector, usually it's a spanning set, right, of vectors, and the span is just all the vectors that we've chosen to define this space. So in this case, like we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. We have 8 vectors. So v1 ... v8. That is, in this case, the span of the set that we've chosen. And we could have even more, right? We could have up to v100. We could have up to v1000. Doesn't matter. We can have as many vectors as we want. But this motivates the question: how little vectors can we have? Like, how many do we really need? When we do have 8, is that better? Is it worse? Are we wasting time putting that many vectors? Is there a reason for us to? So that brings about the idea of a basis. And I mentioned it when I said standard basis all that time ago. And the basis is the minimum amount. So the minimum amount of vectors needed to span a space. I'm going to put subspace. Because every space is a subspace of R something. Unless it is R, then R1, 2, 3 are all subspaces of R. The almighty. Infinity. The cosmos. So we're trying to find the minimum amount. Now it turns out, as I have mentioned before, that the minimum number of vectors needed is equal to the dimension of the space. And you can't have any less than that. So if we have R3, we need 3 vectors. If we have R4, we need 4. If we have R2, we need 2. If we have R1, we just need 1 vector. And the other thing is that you have to be careful about this R3. I really shouldn't say R3. I should say like dimension 3 or something, because different level spaces can exist in each other, which sounds kind of strange. But if we take a look at R3, right, here's our R3, it's in 3 dimensions, like this is where we live, right? We can say that R3 is this whole space. That's the most general way. And we can take, 3 vectors who have certain properties, right, which we can talk about next. And we can say that these create the basis, a basis for R3. Maybe not the standard basis, but like the standard basis is also one of the bases. Oh, and the other thing is that any given space can have a lot of different bases. Usually there's one that we'll come across that's the easiest to because of the way we do the math, but it's not like there's not only one right answer. If you wanted to make a normalized basis, then there would only be one answer. But no, actually that's a lie. There would still be multiple answers. Don't listen to me. There'd be less answers. So yeah, in R3. But the thing is, right, we can still have 2-dimensional objects in R3. And we can still have 1-dimensional objects. So if we wanted to have a plane that goes through the origin, like that picture up there, we're not trying to span all of R3 with this. So if we wanted to span this space within R3, we would just need 2 vectors. So even though it's 3-dimensional, right, it's got 3 x, y, z, you still only need 2 vectors, y1, z1, for this. And the same for a line, or not the same, but similar for a line. If you wanted to span this line, you only need 1 vector. Oh my god, I really want to write x, apparently. No, don't cut the entire layer. So there's one other part we have to talk about for a basis. These vectors, right? We kind of talked about this. The idea of linear independence, right? Linear independence can be thought of as, vectors not being combinations of each other, but it can also be thought of as vectors being sort of significant, or at least that's the way that I like to think about it, is that when you have those vectors in a clump, if they're all linearly independent, they're all telling you different things. They're all constraining you along a new axis. Because when we're trying to define a space, like let's say we want to define a plane, we know that we have to constrain in one direction, but that the other 2 directions you can move around on. So that idea of like, where are we constraining, like, and how it relates to linear independence is really important. So the idea is that for a basis to span a space, the vectors in it need to also be linearly independent. Which kind of makes sense, right? Because if you have 3 vectors and 2 of them are telling you the same thing, you don't really have 3 vectors, you only have 2 vectors. So now we can talk about an interesting thing. Let's do a little example. So let's pull up 3 vectors. Let's do 3, 4, 5. No, let's not do that. Let's do 1, 1, 0, 0, 1, 0, and 1, 2, 3. Now the question is are these a basis for R3? So if we think about our definition of basis, we got 2 things, right? We know we have to have at least 3, or we have to have it, yeah, we have to have 3. We can't have less than 3 because that's not a basis. We can't have more than 3 because then we're having too much information. One of those vectors is telling us something we don't need. Because each of these has to span the space, remember. So if we have a vector that spans the space and we already have 3, then we're going to have a redundant vector. Not that it's like bad. They won't just be like, oh, this one actually doesn't span the space. Then nobody would lie to you like that. I mean, maybe they would if they were like kind of evil, but I wouldn't lie. Okay, so we know that there's 3, so that's a good start. Now we also have to test for the linear independence part. So we're going to go back to that little matrix example we did where we were testing for linear independence. And we're going to chuck these boys in a matrix. We're going to test to see if the variables we solve for, if those are all 0. That is what we're looking for, right? For them to all be 0. So let's do this. Let's do R2 minus R1. R2, so 0, 1, 1, 1, 0, 3. And I'm going to go ahead and divide this by 3 as well. And very simply, I'm not going to write it out, but you can see that this is going to equal the identity matrix. So we have found 3 vectors who are linearly independent that span the space. And the reason why we know that they span the space is because they are in R3. That's another question that could be asked, like, do these span R3? Then what you'd have to do is you have to say, for all these, if you add them up, let's call this one, oh, this will be so annoying, A1 plus B1 plus, or A1 plus C1 has to equal any number in R, and then A2 plus B2 plus 2C2 has to equal any number in R, and then A3, so C3 has to equal any number in R. So that's okay. C3 can equal any number in R. Is this right? I think it might just be A. But yeah, basically you have to go through this and then you can prove that they're all spanning. It's a little bit easier when it's R3 and there's not a specific set. Like, because for example, you could say, are these a basis for this plane? You know? And they'd have to be linearly independent and also describe the plane in that case. But let's do an example with one that won't be a basis. So if I change this to 2, 2, real simple. Then our matrix will look like 1, 1, 0, 2, 2, 0, 1, 2, 3. And when we row reduce this, we're going to get this minus this is 0, or sorry, 1, 2, 1, 0, 0, 1, 0, 0, 3. So this will go to, I'm not writing the steps down, don't do that, but. So we have a row of zeros at the bottom here, and we'll do that. This is our row reduced matrix. Now, looking at this, we can tell a couple things. Like if we didn't know what these formed, right? Let's try to analyze it. So, we know that there's 2 pivots here. And that means that we have two vectors who are actually telling us different information, right? And one of those vectors is a phony, is just trying to fit in, which is the 2, 2, 0, or the 1, 1, 0, depending on how you look at it. And actually, interestingly enough, we can also figure out exactly which of the vectors are those important vectors. If we match up the leading ones that we have to our original set of vectors in the order that we have them in, we know that this one here, the first one, and the third one are going to be the useful ones for defining this space. That's going to form the basis of our space. Another way to describe the space, quote unquote, that we are defining is called the image. So it's like, what are we forming, basically, which kind of makes sense. It's like an image. So we know that we have two vectors here, so we know that it's going to make a plane. That is our image. That's kind of how our vectors are going to look, what they're going to look like. There's a lot more to talk about with that. But another thing we can talk about is the rank. So this is kind of it's not too bad. Basically, the rank is the number of linearly independent vectors you have. In this case, the rank would be 2, right? And that is going to be the dimension of our image, or the dimension of our space that we're defining, which makes sense, right? If we only had one vector, we'd be making a line, and that line would be dimension 1. And that means the matrix is rank 1, and we're getting that out, right? So the thing about rank, and the reason we care about rank, is there is something called the rank nullity theorem that tells us about some disappearing vectors. Because the issue that we have, right, is when we create this space with this matrix, we're going from having 3 to only having 2. And these right here, these are getting got. They're getting squished down into nothing. And we want to, it's very useful for us to figure out where that, basically, from moving from 3 dimensions to 2 dimensions, what happens there? Like, which vectors are going there? I forgot to mention this, but, and this is kind of a little bit later, actually, but you can multiply matrices, right? And the way that you can think about a matrix is, how much do I want to say about this? You know what? Fuck it. We can talk about this. Another way to think of a matrix, right? So we can think of a matrix as defining space. We can think of matrices as, right, an abstraction of a system of linear equations. Because this space is really our solution space when we think about that, right? Like, this is where we're going to. You can also think about a matrix as a function, or a transformation, right? Because we're starting with something and we're going to another place. And that's really all a function is. You have an input, you get an output. So we can put vectors into this matrix, quote unquote. We can like feed this matrix a vector. And we can see what it does to the vector by multiplying this matrix by a vector and sort of applying that function or applying that transformation to it. So, in that case, right, or let's see, what's a better way to talk about this? Essentially, we're starting out with x, y, z, right, for this given matrix, and we're only ending up in a well, it's not really x, y or anything, but we're only ending up being able to move in 2 of those. So we've started moving in 3 directions by moving 3 directions, and we've gone to being able to only move in 2. That's where the rank nullity theorem comes in, because null, right, like in coding, is 0, or like nothing, right? It's British, or maybe British is nil, I don't know. But anyway, null, the null space, if you will. And you're like, Damie, what the hell? We've been talking about spaces as things. How can space be 0? And you got a good point. Our image is over here, right? This happens after the transform. Happens after we do all our stuff with our matrix. Our matrix is defining this space. But that space is kind of exclusive, right? So what we can look at is the before picture. And in R3, our null space will be a space of all of the vectors that don't make it onto this plane, that go to 0, that go to the null. So because we can't have any vectors that go, like we can't have a vector that goes up here, right? We know that because it has to be on this plane. So we can only have, and this is also an infinite plane. Doesn't look like it, but they can only be on this plane. So like, what about a vector that goes like over this way? Too bad, this guy he doesn't get to take the journey. What about a vector that goes this way? Nope, can't do it. Can't take the journey. So we need a way to define those vectors that can't come with us. And that is the null space. So in this case, because we have a plane, what our null space is going to look like is a line. And you're gonna be like, why? And it's a great question. One of the reasons why, one of the answers I can give to that is the rank nullity theorem. So the rank is the dimension of our after space. The nullity is the dimension of our null space. You can also call it, this is a nullity, or just the dimension of the null space. And the theorem is that the dimension of the original whole space that existed, the R3, right, because our matrix is in R3, that's defined by the columns. I forgot to mention that. There's 3 columns that we've defined. The dimension of the original space minus the rank equals the nullity, or the other way around. So we have 3 minus 2 equals 1. So that's how we know our null space is going to be a line. The other way to think about it is this, and this is a much less geometric way to think about it. Let me put on music again because it stopped. Where did my music go? Okay, the other way to think about it is this. We want to figure out which vectors are the ones going to 0, right? So when I say not making it over, right, the vectors still do make it over in this plane that exists in our after. I'm going to start drawing it on the other side. So here's our before. This is our lovely set of inputs, everything we can input into this function, right? Which is any vector that has 3 components, because our matrix is a 3 by 3. And our output is this plane, right? Which can look like this. Has to go through the origin. Pretend that goes through the origin. It doesn't really look like it goes through the origin, but maybe it does. Figure like that. Our output is still vectors in R3, but it's a more specific set of vectors, right? So if we take a look at it like this, and we know that these vectors are getting squished down to 0, because if like, you know, if our in is, let me draw it in a different color. If our in is a vector, geez, here, and it goes to this plane, it's gonna go down to 0. It's gonna get squashed, because we're kind of taking this whole, you can kind of think of it as like a cube in a way, like this whole thing is a big cube, and we're turning that cube into just a flat plane. So as we squash the space, those vectors are the ones that get squished. Anyone that's not on the plane. So the way that we can figure this out sort of mathematically is we want to say, what vectors are the ones that are going to 0 after the transformation is applied, after we're doing stuff to them. So after we do a v, right, a times v, do we apply it, which one of those equals 0? And that is the exact same thing as saying, here's our matrix of, what was our matrix? I already forgot. 1, 2, 0, okay. 2, 0, 0, 1. That's like saying each of these rows equals 0. And in reality, if we were trying to write it like the augmented matrix way instead of just the coefficients, there's a reason we don't have to. We could just write the whole matrix like this, right? The reason we don't have to is because like 0 times a number is going to be still 0, and 0 plus 0, since all these are, right, all these columns are 0, rows are 0, they will always be 0, so we can just leave them out to the end. So in this case, we're going to say x plus 2y equals 0, and z equals 0. Now, what does this mean? Well, that means that any vector with z equals 0 is gonna get squished to 0. And that, for this, x equals minus 2y, we can write our solutions as a vector. We can say minus 2y, or let's do it like this, x, y, z, right? We can just write them as a vector if we want to. But now if we substitute these things in, we can say negative 2y, y, 0. So any vector with the form of this is going to go to 0. So if we had like negative 2, 1, 0, that would go to 0 if we were to draw that. Negative 2 this way, 1, or negative 2, 1. That's going to go to 0 here. This plane is definitely not right that I drew. And another really cool thing we can do is we're trying to draw a line, right? We know that this is going to be a line, but it's kind of hard to see that this is a line, I guess, like this. So what if instead of writing it like this, where these are the numbers that we're changing, what if we brought those out and wrote it in a little bit of a different way? So I'm going to factor out a y, essentially. And we can now see that this is our line. The line defined by this vector tells us in this space, so let's say that this line is negative 2, back this way, 1, 0. All the vectors on this line are going to go to 0 when we have this transformation. And if we were to have, like, let's say we had another free variable, right? That would change our space that we're creating into only being defined in one dimension. So that would have to be a line, and then our null space would be the thing that has the plane. There's a whole, there'd be a whole plane here that went to 0 over there. It's not a great explanation. It's very scattered, but hopefully there's some good stuff in there, some followable stuff. I do really like this I like thinking about like the definitions, like a matrix as a definition of a space, more than just a system, because it's like you're defining a space of solutions essentially. You're defining like a list of outputs, because solutions are just outputs, really. I'm a programmer by you know, childhood, so I like to think of things as functions instead, because I feel like they're a little bit more approachable that way. You don't always have to know exactly what a function does. Sometimes it's just useful to know how to use it, right? What its inputs are and how it outputs. And that's a lot about matrices and linear algebra, is setting up, like knowing how to construct matrices so that you can make them give you the outputs you want. So, let's see. Another great thing we can talk about is the idea of... Let's continue on the idea of transformations. So let's draw a little in and out again. In and out. So let's say we put in this vector. We don't know what this is, a new matrix that we're multiplying it by. We don't know what it does. And let's say we get out this vector over here. One thing that's really helpful to know about a matrix is if we can only go this way, or if we can also go this way. Hey, Vintage Luigi. How's it going? And this is obviously super useful for a lot of different reasons, because, you know, maybe you have some outputs and you want to be able to do the reverse to them. You want to see where they came from. And a lot of the times we like working with invertible things because we can do exactly that. We can go back and forth from each space at will. I spoiled it a bit here, but if you can go back and forth, that is then an invertible transformation or an invertible matrix. And that means you can take your output and go to your input. The way I like to think about it, without even doing any math, is sort of like, well, there's a way that you can think about whether a transform or a matrix is invertible or not. Let's say you're going from R3 and you're going to R2. So you're in sort of like a cube or something, or hyperplane, whatever. And you're going to a plane like that. Oh my gosh. Oh, who followed? Wait a second. He runs over to my little... Oh, thank you for the follow. Oh god, I'm gonna say a name wrong. I've mispronounced so many names. If I mispronounced your name, I'm sorry. Musefi? Musefi? I'm the guy. Okay, see, here's the thing. Twitch streamers are like, oh, I read names wrong. And I'm like, I just read names wrong in general, because I went to like IKEA, and you know how they have like the, you know that they have the thing that's like as is? I was there with my mom once, and I was like, oh hey, can we go over to ASIS? She was like, what? And I was like, oh, you know the place where they like sell stuff for like cheaper because it's like people return it or whatever? And she's like, do you mean as is? And I was like, oh no, I did it again. I goofed it. Yeah, as is. I think about that a lot. I think about that too much. Sometimes it just comes back and gets you. But anyway, back to the linear algebra. Let's say we have a space that the input, right, we're going from the in, is R3, and we have lovely, beautiful vectors in R3. Oh my gosh, thank you for the follow, Kata. A lovely full vector in R3, and we're getting out an R2 vector, right? So that means that it's gonna have 3 components, but our space is defined by this plane. Well, actually, you know what? Let's not even do this. Let's not even think. Let's literally go to straight up R2. which you can do. You can change, let's say, did I draw the vector? I didn't even draw a vector. Okay, let's go there, and let's say that it gets turned into the standard basis. It's one of the standard basis vectors in R2, why not? The way I like to think about it is like anytime you're changing dimensions like this, or anytime you're really changing you're losing information from a vector, right? In this, it's like if you had, you know, I don't know why I think about it this way, but it's like if you were going, you know, on an airplane or something, and before you went on the airplane, you had to like get your arm chopped off. Like, there's no way you like can come back the same. Like, you can try, but like your arm is gone forever. Like, so moving down a dimension, or like moving to a place where you're losing information from a vector is essentially how you create a non-invertible transformation. But moving up, like if I was going from R2 to R3, that's called, I think it's called embedding, where you would then have this vector that's just like chilling in here like this. Or I guess it should be chilling in here like this, if this is X and Y. And then you can always go back, right? Because you just clip off that little extra 0 that you put at the bottom. And that's okay, we can do that. But yeah, we do want to figure out whether a matrix is invertible or not. And the way that we can figure that out is through, big surprise, through linear independence. And this kind of makes sense, right? If you are in the same vein that you're going from R3 to R2, and you're losing information like completely, like you're literally just losing a whole value. If you're going from an R3 space to a plane, you're still kind of making that that distinction. So if you have a vector that's redundant in your basis, or not in your basis, if you have a basis that's actually smaller than your initial set, then you're still going to be losing information. But we can do a little example. It's pretty much the same as we've been doing. If you haven't noticed, a lot of linear algebra is just put all vectors in matrix as columns. Row reduce matrix. Figure out what your thing is. Let's do, okay, I'm gonna do 3 vectors. Let's do, does anybody have any vector suggestions? We'll do 3, 2, 1. I'll flip it and mix it up a little bit. 1, 0, 0. And then 1, 1, 1. Yeah, that's like not initially. Okay, let's do a couple things. Let's find, let's say, are these a basis for R3? A basis. Actually, let's not do that. Let's actually do a different thing. Let's say find the image basis. Good one. Find the null space basis. And let's say is the matrix / transform invertible. Invertible. All right. Okay. Okay, chat. Where do we start? First step. You know it. You love it. It's a thing we always do to matrices. We're gonna row reduce this motherfucker. I'm going to flip the first and the last row because I'm lazy and I don't want to do more math. So we're gonna flip that. And then I'm going to do R2 minus R1, R3 minus R1. 1, 0, 1, 0. No, that's 2. That's 3. 0. That'll be 0. That'll be 1. There's 1. 1 minus 2 is -1. 1 minus 3 is -2. I'm gonna flip these two. Oh, look at this. This is working out so well, and I didn't even plan this. Okay, 1, 0, 1. 0, 1, -2. 0, 1. Oh, look at this. Look at this. They're literally independent. So beautiful. Okay, yeah, I don't even need to do the rest of this. Well, okay, maybe that's not the best. Okay, well, we can still do this. A lot of times, we'll modify it after to make it different. But we'll do this way. Okay, find the image basis. So our image basis is actually just, right, our transform is created by these columns. So our image basis is going to be these 3 vectors. None of them are redundant. We're going from R3 to R3. Everybody is happy. We've lost no limbs in the process, which is great. Find the null space basis? Oh, well, you know, it's just gonna be 0. Because, that is 0. Right, there's no vectors that don't make it over. Everybody has a place in this new wonderful space that we've created that's 3-dimensional. It's probably just like turned or skewed or squashed or stretched a little bit. We could actually probably break this down into like what it does. Oh, we could, you know what? We should do that next. We can do that next. That'll be fun. Oh, I don't even need to do that. What am I talking about? Let me show you how we can do that, chat. Okay, so let's talk about our in and out again. So our in, I've just been kind of like not drawing the space because like how do you draw R3 or like drawing it as a cube? But if we have our in as R3, that's gonna be this standard basis vector. Let me draw them in a different color. This vector right here. This vector right here. And this vector right here. Right? Or x, y, z. So let's try and figure out what these guys actually, what happens to these guys. I haven't gone over matrix multiplication because I don't think that that is something that really needs to be talked about. It's very just formulaic. I mean, if somebody wants me to explain it, I'm down to explain it, but the long and short of it is that to multiply matrices together, you take it's like a dot product. So you're gonna take this dotted with the first column, this dotted with the second, and this dotted with the third. And you do that for each one. So in this case, right, because 3.1 is 3, 2.1, 2, we don't really have to do that much work. It's just gonna go to that. So I'll call this x, this y. And see, we can see that, let's do the x one first. X is gonna go to, oh shit, I lost that color. God damn it, I liked that color. Is that like way lighter? It's a little lighter. Maybe it's not. There we go. Shit. Okay. That x is gonna go to the 3, 1, 3, 2, 1, because that is what we start. This is just the order of our columns here. So x is gonna go to 1, 2, 3. 1, 2, 1. Oh boy, this is gonna be hard to draw. Something like that, I guess? No, like down a little more. Like that. Something like that. Y is gonna go to 0, 1, 0, so that's gonna take x's place, actually, funnily enough. That was z I just drew, sorry. And then z is going to go to 1, 1, 1. So that's like here. This is an incomprehensible picture. Sorry about that. But you can see that we've kind of like taken, if you use, I wish I had hand tracking, don't have it, just gonna have to use your brain. If you like point your finger in the direction of Z and you point your thumb in the direction of Y and the other one in the direction of X, you can kind of see that like we're turning it. If you have your hand, right, your thumb would be pointing to the right. We're kind of turning it on its side and like stretching it out in the X direction. We're kind of flipping it over itself, so that X is now on the right of Y instead of on left. Yeah, we're like switching the right-handed to left-handed coordinate system, basically. But yeah, so this is a really nice thing, right? Because we can undo this. And let's do the matrix for undoing it. The way that we do that is there are a couple different ways of doing it. You can do. Oh boy, I don't remember how to do it that way. No, that's not for 3x3s. There's a special way to do it for 2x2s, but if you just, the abridged version of this story is if you take the matrix and while you're row reducing it, you plop on an identity matrix on the right side and you also do the row operations on that, then the thing on this side will become your inverse, so A inverse, and the thing on this side will become the identity matrix. Because the definition of an inverse matrix is A times A inverse equals the identity. So for this to be true, You've been live for more than 4 hours? I have not been live for 4 hours. I've been live for 2 hours. Unless my clock is lying to me. Hydrate? Oh, thank you, actually. That's so real. It's only been 2 hours, Umbra. I didn't start at 12, I definitely started at 2. Umbra went to the shadow dimension. Umbra went to an uninvertible transformation, guys. Umbra came back different. That's funny though. Yeah, I've not been live that long. I've not been talking about math that long. I was gonna say, that means a squared equals a in. No, that's not right. There's a proof here. I don't remember it. I'm not gonna try and do it. It's actually probably really simple. It's just like the a times. I think it's the, like a times the identity equals the inverse times a inverse. I want to say, but I don't think that's exactly right. Oh, wait. I think if you multiply both sides by A inverse, yes. So if you multiply both sides by A inverse, you get A times A inverse equals I A inverse, and then this is just I. So I times A inverse equals I A. What the hell? What did I do? I don't know. It's fine. I'm normal. Oh, no, it's just, yeah, wait, what? I don't know what I'm trying to prove. It's fine, just trust me, it works, okay? I'll prove it in a short if somebody ever wants me to prove it. I don't like just trust me, bro, in anything, but, I also really don't want to find the inverse of this right now, so we're not gonna. I'm trying to think. Inverses, we can talk about determinants. To be honest, determinants are useful. But like, What are determinants? Yeah, we do have to talk about determinants. Okay. What is the best way to talk about a determinant? It's been a long time since I had to like know what a determinant is. So in other news about things we can know about matrices. Sometimes it's good for us to kind of get some information on not like the spaces that it creates, but stuff about the relations between the numbers in the matrix, right? And it turns out that we can actually figure out a specific type of operation that we can perform on a matrix, like kind of like a function in a way. Not like a transform or anything, but like just like a thing we can do to a matrix, sort of. That will let us know whether or not a matrix is invertible, which lets us know whether or not the matrix is linearly independent. And that's very good. It's a very good thing, because if you put in a matrix to a computer, it can tell you real quick, just by a simple calculation, whether or not you have linearly independent vectors, which means that it'll tell you whether or not you have a basis for a space, right? So let's do that. Let's take a look at what a determinant is. Let's do it on a 2x2 because it's the best place to start. So the idea of a determinant is very simple. And it sounds a little strange, but it's just like a formula you do. So for a 2x2, if this is A, B, C, D, you're gonna do A times D minus B times C. That's all it is. That tells you the determinant. So in this case, the determinant is 1 times 1 minus 6 equals -5. Now that does not equal 0. So let's see, if we took the linearly independent version of this, we did this, this would be 1 minus 0 equals 1. It doesn't equal 0 and it doesn't equal 1. If your determinant equals... If the determinant equals 0, then it is... If your determinant equals 0... Oh, wait, let's do this with... So we see that it equals 1. That means it's good. It is... We know that, so 1 is linearly independent. And then let's do this with 1, 0, 0, 0. That would be 0 minus 0 equals 0. So for determining whether it's linearly independent or not, it can't be 0. So, long story short, you do this thing. This is the formula right here. And if the determinant doesn't equal 0, then you're linearly independent and you're invertible. This is kind of a caveat, as long as square, because you have to be square, right? Because if you're linearly independent, but you only have two vectors and you have three variables, then you're gonna be cutting off somebody's arm on that plane ride, right? You can't do that. That's why I always leave a note. No, but am I invertible? Oh, I could be I feel like, this is a question I ask myself about various people I meet. But I also don't think everybody is a determinant. I usually assign different people different math things in my head. I don't meet a lot of matrix people, I'm gonna be honest. I think... Are you invertible? Oof. I don't think of you as a matrix. I think that, oh, maybe there's one person who I know who's a non-invertible matrix. I think being a non-invertible matrix is a bad thing. Is the thing. If you're the kind, if you're like, hey, Damie, what math thing am I in your brain? And I say, oh, well, you know, you're a non-invertible matrix. I'm like, that means, like, to me, like, you're stuck. You go somewhere and you can't come back. You can't change. You can't, like, grow. You can't, like, recurse. An invertible matrix is like you know, I don't assign a lot of people matrices because a matrix is so general. That's like me going to somebody and being like, yeah, you're a function. It's like, no, you're not a function. You're like a circle or like a parallelepiped, or like you're a sphere, or you're a cone or something, you know? Those are all very specific relations. But a matrix is just like, that's like me going up and being like, well, yeah, you're R3. It's like, no, I can't say that. Matrix until proven otherwise because it's general. Yeah, I think everybody has a matrix that is with them. I do assign dimensions to people, I will say. I will say that a lot of the time I think that I'm in R4 and a lot of people are in R3. So, do with that what you will. But I think that, yeah, I think everybody has a matrix, and you can, you know, like, you can find people's determinants, and like, that's a very good thing to know. I think that a lot of the times, though, the matrices are much more like systems of differential equations because they're changing. They're changing constantly, and you're just sort of changing your variables based off of like constants you have. So finding the determinant of those things is a little bit less useful, as you will see, because we're going to talk about eigenvalues next. But you know, yeah, being invertible is not necessarily always a bad thing. Like in eigenvalues, it's not a bad thing, and eigenvalues are very useful, but I think a lot of the time being invertible is better. Gonna be honest. And a lot more things are invertible, I will say. Like, as you've seen, like, all the examples I just randomly came up with of, like, stuff, like, how many of those weren't linearly, like, independent until I specifically made them linearly dependent? They were all linearly independent, so they were all invertible. That's not a straight line. It's fine. Okay, let's talk about eigenvalues. Eigen things. Let me write it out. Eigen. Like that. Eigen. Eigenvalues. And then we can talk about other things. So, the motivation for eigenvalues. This is a weird little word. You're like, Damie, why are you saying this so much? Why are there so many words that have this weird word in front of them? I'm pretty sure it's some guy's name. I don't know where it came from. Maybe it's like a little funny creature or something, an eigen. I don't know. But what we're searching for, we're on a little mission here, and we want to try and find this. We want to say that when we apply our transformation, right, our matrix, on a vector, we feed a vector into it, that what pops out on the other end is some lambda, this is our eigenvalue, times the same vector. Now this is pretty big, right? Because I mean, if we look at this example, we were putting these vectors in, these things were going wild. These things were going all over the place. A lot of the times vectors just go all over the place, right? When we transform them, when we're spinning them around and shit, right? They're not going to be just themselves, but bigger or smaller. But these vectors, these eigenvalues and eigenvectors are very special because these are the ones that don't change that much. They just get bigger or smaller. So if we were to draw a picture of what this would look like, here's our in, here's our out. We're gonna put in a vector Like, let's make it real easy. We're gonna put in this. And we're gonna get out. Could be a vector that's smaller. These are different cases. It will only be one of these for any given thing. Like, let me give you an example, actually. Let me give a very specific example. It's gonna be exactly the same vector. So, just very simply, what this means is because it's the exact same vector, the lambda that we're multiplying it by is going to be 1, right? Because this is literally just, we're putting in v, we're getting out v. So that means that if v equals some number times v, it's going to be 1. So our lambda equals 1 in this case. And you're like, Damie, what possibly could you do to get this? Well, there are a couple things you could do. But one of the things you might want to do is let's just put in some other bases. Let's pretend it's just an R3. One of the things you might be doing to this space is spinning it. Right? Like, let's say we spun orange over here and blue over here. That vector is going to stay the same if we're just turning it around, right? Now, there are some people and some classes that might have you look at a transformation geometrically and try and figure out eigenvalues. I think that's pretty hard. And there are only a couple transformations that you'd actually be able to do that for, some very special cases. So a lot of the times I won't do it, but I do think it is cool visually to see, like, oh hey, like this vector is like staying the same basically and only growing or shrinking bigger. So we're on the search. We're on the search for that. Now let's try and figure out some math that we can do to figure out what these eigenvalues might be. So I'm going to do a really simple proof right here. I want to solve for v, actually. Not for lambda, I lied. But we're going to use it to find lambdas. So let's group all the v's together. Right? So we want to get all the v's together so we can hypothetically factor it out. So we're going to do av minus lambda v equals 0. Now, I know what you're saying. Okay, how the fuck do we do this? Well, it kind of looks like we could factor a v out, right? So let's just do that. Let's just pull that v out. That works. We're allowed to do that. Now we're kind of met at a strange crossroads here. We have a matrix. This is a whole ass matrix of like shit in here, minus a constant. Now we can't do that. We can't do that. So we're not allowed, right? That's not in our matrix thing. It's like, what would that even mean if you minus a constant? But remember when I said the identity matrix is a tool that we can use to turn constants into matrices. Let's just put lambda times the identity matrix. So what we've just done is put lambdas on the diagonal of the identity matrix, like that. And these are all zeros. So we've done that. So we made it into a matrix, nice. And we've kind of preserved the like uniqueness of it. So now the thing we have to figure out is, we know that v is never going to equal 0, right? Because that's our, well, I mean, it might equal 0, but like most times it won't equal 0. So we have to figure out, well, I guess it's a good question is, for this, what values of v, if we are putting in 0, it's always going to equal 0. So v, we might say that v is always an eigenvector. That might be one way. But then what we can do is we can just take this part and say that equals 0. And so that's how we're going to use, that's how we're going to find the, well, not exactly, actually. I lied. Because we can't have a matrix minus something equals like 0. Like that doesn't, again, it's still kind of the same case of this is a constant. But if we think about this, what did we just learn about that can tell us a number that pops out of a matrix that that we can use to learn information about a matrix and like whether or not it's invertible? The determinant. So if we take the determinant of this whole thing, we can get a constant. And what does this mean? Well, for the determinant to equal 0, it can't be invertible. Be invertible, right? We just went through that whole thing. We're like, okay, this is 0, it's not 0. So that's why invertible matrices are sometimes good. They're sometimes good. Sorry, non-invertible matrices. But I would say a lot of the time I would like an invertible matrix over a non-invertible one. Just the kind of guy I am. Okay, cool. So the idea is that we do A minus this lambda. Here. I mean, I think the idea behind invertible is that it wouldn't be a medical emergency if it was inverted. I think that means your butt is non-invertible. Because you can invert like a vector, or you can like transform a vector, and you can try and get it back, and you can get some information back, but you can never get the full thing back. And I think that if you did that to your butt, it would be the second case, not the first case. You'd be losing part of yourself in that. I don't really know what, but it'd be an important part of you, I think. Or part of your butt. That's a silly question. Things that you can only ask your Catboy math teacher, not your real teacher. Probably our pride. Maybe. Could be anything. Could depend on the person. Okay, let's do some eigenvalues for one of these. Let's do this one up here. 1, 3, 2, 1. This might not work out very well. Okay, so we're trying to solve for lambda. So we are actually literally just going to put a lambda in there. It's not, I don't know if I made that clear, but. So we're going to do a minus lambda in. So that's going to look like this. It's going to go 1, 3, 2, 1 minus lambda 0, 0, lambda. If we do this out, 1 minus lambda, 3, 2, 1 minus lambda. And now to take the determinant, we're going to do the A, B, C, D thing, right? So 1 minus lambda squared minus 6 equals 0. Factor this out. 1 minus 2 lambda plus lambda squared minus 6 equals 0. Oh, damn it. I fucked up. Minus 2 lambda minus 5 equals 0. Yeah, so this doesn't work. But let me think about what would be better. Let's do a nicer one. Because that doesn't factor into, I mean, you can factor it, but it just doesn't factor very nicely. Let's pick a nicer one. Let's do, okay. Let's do 1 minus 1. Three, 1, I think would work. Let's see. So I'm gonna shortcut a little bit. Right, so this is our a minus lambda I, n. 1 minus lambda, negative 1 minus lambda, minus 3. It'll be negative 1. The lambdas cancel, plus lambda squared minus 3 equals 0. Lambda squared equals 4. So lambda equals plus or minus 2. Okay, so what this means, right, is that we have Our vectors that are staying the same are going to be grow by 2. So this one will grow by 2, and one will grow by, the other one might be like this way, let's say, and that one will grow by -2. We don't know what vectors they are yet, though. That is the second part of this question. So we know that if we go back to that equation, AV minus, or AV equals lambda V. So if we plug in, well, actually, I lied about that. If we plug lambda into the A minus lambda, we can actually figure out what those vectors are going to be. You know, I don't have the best explanation for why we do that, because I'm going to be honest, I don't remember. I think it comes from the fact that if A minus lambda in is always 0, and we know that the V like times the matrix is 0, then we can like kind of backwards figure out what the V has to be. So if we plug that, or it could be because, oh, I know why. If we write this, okay, I actually have a good answer. If we write this like this, like I probably should have written, yeah, don't write it like that. Actually, that was wrong to write the vector in front of it because we're multiplying this vector by this matrix. If we have this equals 0, this is just like the same thing as saying AX equals 0, and that's the same thing we've been solving with the null space. So all we have to do is find the null space of the different lambda matrices, and then we're good to go. That might be a lot of jargon, but if you don't understand that, that's okay. Hopefully this example kind of illustrates it a little bit better. So for our lambda equals, let's do 2 first. So we're going to plug in 2 here for our lambda. So 1 minus 2 is minus 1, 3, 1, minus 1, minus 2, minus 3. And you'll see that luckily we did it right, because if we were to row reduce this to find the null space, we're going to get, this is R2 plus R1. We're going to get 1 minus 3, or times minus 1. And then 0, 0. So solving for the null space, which we've done before, right? This is going to be, we know that let's think about what our image would look like. In this case, our image would just be the first vector, right? So the first vector in this specific matrix though, right? Not this original one, because this is where we plugged it in. So our image would look like a line. And that means that by the rank nullity theorem, we started off with 2 dimensions. Our null space should also be a line. So we're going to get x equals 3y. I'll do this a little bit slower. X minus 3y equals 0. X equals 3y. X, y equals 3y, y. And then we pull out the y, and this will be 3, 1 times y. So this 3, 1 is going to be our first eigenvector. And we can check that it's an eigenvector, because the cool thing is, right, we just found that this eigenvector matches up with that 2. So when we plug in this vector to our matrix, we should get 2 times this vector. So we should expect to see 6, 2. So let's see if that happens. So 1, 3, 1, negative 1. And we're going to multiply by 3, 1. Let's do 3 times the first plus 1 times the second, and that will be 3 plus 3, so that'd be 6. And we have 3 times this one plus, or I mean, I guess it might even just, well, whatever. This will be 2. Will it? Wait. 1. Oh yeah, 3 minus 1 is 2. Look at that. And we got 6, 2 out of it. So if we were to graph this in our in would be over here. And let's draw like the whole thing. So the vector that we want to look at is going to be the 3, 1. 1, 2, 3, 1. Oh, why am I drawing this in here? Lol. It's in R2. 1, 2, 3, 1. So there's our vector, right? Our whole space, we live in R2, and we can put anything in R2 into here. And we know that we'll graph the null space after. We know that this vector goes to 1, 2, 3, 4, 5, 6, 1, 2. So it just scales in that same direction it was already pointing in. And our space is now going to be based off of, well, that's not really super helpful to find the eigen like that. But it's going to be that. And then if we wanted to find our null space for this matrix, we could say, do 1, 3, and then this minus this, that would be 0. Minus 4, so that'd be just, this turns into 1, this turns into a 0. That actually is still the, wait, is that right? That seems like it should be wrong. How do you have eigenvalues then? If it's invertible. Did I fuck up? Wait, 1, 3. This minus this is 0 minus 4. Oh, weird. That shouldn't be. Is the determinant? Oh, it's if the determinant is 0, not if the determinant is, wait, but that's still, wait, minus 1. Minus 4, what? 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 Did I do something? Did I do something fucked up? I don't know. Oh, maybe it's that these can't be, these can't be, these individual matrices can't be, can't be invertible, which they are not. Not our original matrix, but our original matrix is invertible. Not interesting, we did it. We just got that. And then let's do for minus 2. Oh, I don't have that much space. I'll do it down here. I already forgot what it was. What was it? It should be minus 1, minus 1, 3, no, sorry, 3, 3, 1, minus 3. No, 3, 3, 1, 1. So that means our x minus y will equal 0, because we're looking for the null space, remember? X equals y. So that will be 1, 1, or I'll do x, y goes to y, y, or x, x. So that is 1, 1 times y. So this is our eigenvector 2. So we started off with 1, 1 right here. And we are going to minus 2 of that. So this way. So you can see our space, it doesn't necessarily have to be in the same like coordination, not coordination, same orientation as it was before. We can like kind of rotate it around, like flip which way the system is, but we do see that these vectors are the ones that are scaled. And you know, like what the hell, let's just like put in like the standard basis. If we put in the standard basis for 1, 0, we'll only get the first column, so that's 1, 1. oh, sorry. The standard basis goes to 1, 1. So you see how it turns there? Turns like that. And then if we want to put in 0, 1, that's going to go to 3, 1, 2, 3, negative 1. So that also turns. That's so interesting, isn't it? So when we like turn this, that vector somehow gets like way bigger, and the it looks like maybe the closer you are to the axis, no, maybe, I don't know. Closer you are to the axis, like the less you get stretched out. But isn't that kind of cool? So we can see, and if we wanted to, it might be useful for us to make these our new basis, our new standard basis, if we wanted to normalize them, because these are the things that aren't moving, right? They tell us stuff about what happens in that, in the move over, because they themselves aren't moving. So if we have, we're talking about bases, right? If we have the same number of eigenvectors as our dimension of our space that we're moving to, we can call that an eigenbasis. So because we have two eigen vectors, they do form an eigenbasis for this transformation, which is pretty cool. And I think I'm probably going to wrap up now, but tomorrow we can start by talking about diagonalization, which is another really cool, really very cool type of thing you can do to a matrix. And it's like where these ideas of like scalable vectors like totally come into play. Because it's like, cool, yeah, we found like some scalable vectors, but like why do we want to, why do we care, right? And I'll give you a sneak preview, but the answer is like, what if we want to take any matrix, like within a certain, it has to have a couple rules following it, and we wanted to put it into only numbers along the diagonal and zeros everywhere else. Because for matrix multiplication, that's like really good, you know, like this is great. Because we just get to multiply each, like if we put a vector in here, like let's say we put in 1, 2, 3, 4, we just get to do 1a, 2b, 3c, and 4d. So if we can find a way to represent matrices like this in some I'm gonna spoil it a little bit, but some different basis, right? Instead of maybe just the standard basis. And we'll talk about change of basis for matrices tomorrow as well. But if we can find that, that would make calculations a lot easier. And that actually also allows us to solve some pretty cool differential equations when we get to that part. This idea about representing, doing certain things in linear systems and being able to find these values will let us find solutions to these systems because of the way that stuff that's linear works. So we love things that are linear, and we love things that like don't change or just are scaled. So yeah, I hope you guys found that a little informative. I know I was a little bit scatterbrained, and there are definitely things that I would like to explain better, and also, you know, maybe not in 2.5 hours, that was like 5 weeks worth of content. You know, maybe don't do that next time, but I really do think some of this stuff is pretty straightforward. And I'd love to do lectures on it, like actual lectures. But I think it's also like more fun for me to do lectures like this that are a little bit like more scuffed, I guess, because like it helps me practice, it helps me like get better at just actually understanding what I would want my lecture content to be for these lectures. Drown him Friday? Okay, I'm gonna drown. 1 second. I have some real water Buy me. Sippies. I can't wait till I put a little Drown Him Friday toggle on my model. Oh, it's gonna be so cute. He's gonna be awesome. Alright, well, I'll be back tomorrow. Yeah, I'm excited to finish this up. And we'll probably do a lot more like problems because I think that doing them is pretty good to do. And I need to practice them. I don't know when. I might stream later. Because I think I have like a review thing I'm going to at like 12. So it might be like a late night stream for you EST people. But I will update on my stream schedule. I don't know if you guys saw it, but haha, I have a stream schedule now that's like I can change. It's like always on the web. It's on my site, which I don't know. I really like it. I feel like it's gonna be way better than posting it on Twitter. Just because like I can update it really quickly and like I don't know. I don't like having to change out all the PNG stuff by hand, you know, so it's like I can have, I think it's good. Here, wait, let me like show a little picture of it real quick if you haven't seen it. Let's see. Also, I haven't been able to play Minecraft because the fucking virus wave came out. So be careful if you play modded Minecraft. I don't know if they fixed it yet, so I've been in B withdrawals. I'm actually so worried about coming back. Okay, guys, wait a second. I need to be a nerd for a second. I am so worried about coming back on this server because my bee population is going to be actually uncontrollable. I don't know what will happen. I don't know if they just started like spewing out of pipes because I think that's what they do when like the chests get too full. Because I had so many bees. I don't know how to express to you like how fast my bees produce things now. And I had to like go in like once a day to like just clear out the system. And I haven't played for like 4 or 5 days, or it feels like that. It's probably been like 2 or 3. No, it's been like, actually it's been since Wednesday. So, but yeah, that's my stream schedule. I'm probably gonna change this one. You can see it says 2 p.m., but it will probably be closer to 5 p.m. Bee infestation, literally. I also don't know what to do with all my extra drones because I have... Did I delete my Twitter? I did not delete my Twitter. My Twitter is at... I changed my handle though. Maybe I shouldn't open my Twitter on stream. 1 second. I'm at damie v tutor, which is... I think I'm also going to change my Twitch handle to that. But I didn't delete my Twitter. I'm right here. I don't tweet a lot. Oh, dead link in bio. Thank you. I should actually change that. Oh my god. I don't tweet a lot, so, you know. A lot of it is just me liking VTuber rigs, I'm gonna be honest. Because I need to rig soon. I'll change the bio though right after this. But yeah. This will be more up to date. It's just because like if you can't see it because like I have a Twitter extension on, but like a lot of my posts were just like stream schedules and it was like so annoying and I just didn't want to like I had things like this which were like way cuter where I would just like post about going live, but like I don't know, maybe I'll do these. I don't know what like the best, I feel like pinging on the Discord is like the best way to like get people, but like look, I just would have like tiny schedules like these and they would be so annoying because they'd take up my whole media tab, but maybe not. Maybe people liked them, I don't know. I feel like this is like really cute. Anyway, I'll see you guys tomorrow. Hopefully my voice is a little better by then. But no promises. Finals on Monday, finals on Tuesday, final on Tuesday. I have a 7 a.m. linear analysis final. Hopefully it goes okay. My voice is always good? Oh, thank you. Yeah, 7 a.m. is really rough, but apparently the apparently the same guy taught at 8, because I have an 8 a.m. math, and then like we have to have a final at 7 to 11, or 7 to 10. And apparently he showed up like at 7:30, so like maybe it'll be fine. Maybe he'll just show up late. I gotta like make sure I can get up. Oh shit, I don't even know where that final is. I'll have to ask somebody. Come to think about it, I don't know what physics final is either. I have to study physics too, but like yeah, I wish I could, God, I wish I could stream more, y'all. Next year I will actually be able to stream more because I'll have my own room, but I did get my schedule, and I have classes like till 6, so it'll be later. But I feel like 6 p.m. PST is not actually an awful time to stream. I do know there's some people like Bug who like wouldn't be able to make that, but VODs will be done way better. I do not have enough computer space to just keep all my VODs, but I've been waiting to upload all of them on the YouTube. So VODs will be a lot better to watch next year and over the summer too, if you want to watch backlog Damie content or just like Damie gaming content. What else? I've been teasing a reveal for a while. You guys probably know that I'm doing it, but I will say, for the people who are here, because you guys are so awesome and like came to lecture, that September is my gentle date for when I want to have debut 2. So it might not happen, but I really would like to have everything together by September, and I think I probably should be able to do that. So that, I'm trying to think if there's anything else. No, I'll see you guys tomorrow. Oh, cool. Yeah. I'll definitely be putting out more stuff about it when, I don't know if I want to do a model reveal. I might. If I think it would do numbers, I would. But like, yeah, honestly, the rigging on my model I think is for like an indie rigger. And also, this was one of the first models I did. I think it's really good, actually. Like, not to toot my own horn, but like, I like looking at my model a lot. Except for the mouth. I have to do a lot of tracking, calibration and stuff. Gonna look into vitamins, stuff like that, but... Yeah, and stream overlays will be different. You can see that I like my old, this setup, but it's so like minimalist that like I didn't have time to redesign it this year, but I probably would have if I had the chance. I want to do interact. Oh, there's so much cool stuff I want to do. But also, I will say that I will probably be doing it in waves, and I'm also not going to reveal all of the tricks that I have planned for my model on my debut. So there'll be some stuff that like you guys get to see like just as I stream more. That I'll just be like, oh hey, look at this cool thing my model can do. And you're like, wow, you know? So, because I don't know, I don't like people like spoiling all their toggles and stuff. So, anyway, all right, I will see you guys tomorrow. Maybe late at night, maybe late night Damie after dark. Probably not, unless Umbra comes on. But Umbra's usually around at the night, so maybe. God, I wish I could play Minecraft again, but we'll wait for that addiction to start back up when I get home. All right, see y'all later. Take it easy. Bye.